Thank you for coming to and reviewing this discussion that involves discussing discrepancies between theory and observation, particularly two particular issues in astronomy. Before we get into the nuts and bolts, I wanted to go in over a little bit of background and give some context to this discussion with some points. In the 2nd century, Ptolemy came up with his geocentric version of what the movement of the planets and the solar system looked like. And they were complicated because with geocentrism in place, the planets don't really behave very well. And they move back and forth occasionally across the night sky. So things got complicated. In the 16th century, Copernicus comes along and he simplifies that by correctly positioning the sun at the center of the solar system. Things are then much simpler, almost circular orbits around the sun. You'll notice here that we go out through Saturn because Saturn is the last one that can be seen by the naked eye. And then this last ring is everything else out there in the universe. A century later, Galileo comes along and starts to produce improved technology. That makes things a lot more easy to do and more accurate to do. So lots of data is collected, people like Tycho Brahe, which ends up with Kepler being able to come up with some laws based off of the large quantity of data that had been collected thus far. And particularly just wanted to point out the second law of Kepler, where, of course, the area that is swept out by a planet in its way around the sun is consistent for a consistent period of time. So in this case, on the left, we've got an area that's closer to the sun, of course, of a 1-month trip. And obviously the trip there is a lot longer in distance than the trip that's on the opposite side, far from the sun or farther from the sun. And the reason for that, of course, is that the planet is actually moving faster as it gets closer to the sun and moving slower as it gets further away. Important for our discussion. In the 17th century as well, Newton comes around and he improves upon Kepler, creates his 3 laws, as well as the universal law of gravitation, which we've been studying this semester, as shown here. You take those 2 together, and you've got some tools. In 1781, William Herschel and his sister Caroline discovered Uranus by accident, just observation, lots and lots of hard work. However, fairly quickly, in looking at Uranus' orbit, astronomers noticed that the orbit of Uranus did not behave very well, didn't behave according to what we would expect from, for instance, Kepler's second law. Thus, the search for an 8th planet began. The orbital interactions between planets are very complex, but at their core are the laws of Newton and the laws of Kepler. And this image here, I'm illustrating how that comes into play with the force that is on one planet by the other, affecting the velocity and the change in momentum. In 1846, Urbain Le Verrier used that information and used those laws to calculate the expected position of Neptune, approximately. Urbain Le Verrier then shipped off his calculations to Johann Galle, and it is said that about 30 minutes after Johann got these calculations, he found Neptune pretty much where Le Verrier had predicted. Then we have another discrepancy of a similar nature. As early as Newton's era, everybody had begun to notice that the orbit of Mercury precessed around the sun. And precessed means that the orbit itself, as illustrated here in this artist drawing, is moving around the sun as time goes on and as orbits are completed. To explain this precession with Newtonian mechanics, Le Verrier and others required that there be another object, so that they immediately began looking for another planet in the vicinity of Mercury's orbit. And In 1859, Whoopi Leverrier reported that the object had been observed. They found it. The planet was ultimately named Vulcan. Of course, we know Vulcan doesn't exist. And part of the reason is that Leverrier's calculations were only partially able to solve the precession problem for Mercury and still left about 43 seconds a century unaccounted for. And to save the day, in 1916, several decades later, Einstein published his general relativity, but he needed observational proof for the assertion about space-time. There were several different possibilities, but in 1916, there was only one possible observation that confirmed it with readily available data. In general relativity, and when it was published, Einstein actually dedicated one whole section to Mercury's precession, and this is in German, but I've highlighted in the red circle there that he actually did confirm that the precession 43 seconds was explained by the bending of space-time. For a better layman's version of all that I've just said, please see a video by Dr. Becky. So, did Einstein actually solve the ultimate puzzle for astronomy? I don't know. But in 1931, Georges Lemaitre published his Big Bang Theory. There's an illustration of that to the right, a little fuzzy in my copying it over. But a singularity at the beginning of time, and the universe explodes. And as time goes on, it continues to expand, as you noted by the levels there. However, that expansion was, of course, affected by gravity, and calculations were made in the later part of the 20th century that really the expansion was ultimately going to be affected by gravity. It would be slowed down, and ultimately collapse would occur, back to a singularity, there possibly another bang, another bang, another bang. However, in 1990, the Hubble Space Telescope was launched. 8 years later, after 8 years of observations, the results of the study were published that showed that actually the expansion of the universe since the beginning of time had been continuing to grow. And in fact, it was expected to continue to grow, because it was accelerating, not decelerating. What's the explanation for that? Dark energy comes in to explain this continuing expansion. We don't know what it is. We don't know what it looks like, tastes, smells, nothing about it that we know, other than the fact that it's responsible somehow mysteriously for this continued expansion of the universe. So people like me aren't necessarily satisfied by that. We're laymen, and it just gets a little mysterious, a little hokey pokey, little bit too metaphysical for us. And we find some allies even witin the scientific community. I found one, this article from 2019 by a group of Greek astrophysicists attempting to explain that there are other ways to deal with the problems that have been uncovered, and in fact they can enhance general relativity to the point that they no longer need dark matter. So who's to say if maybe eventually someone can come up with an explanation that doesn't require dark energy. And of course, that doesn't necessarily mean that general relativity goes away, in the same way that Einstein encompassed Newtonian mechanics within his model. Then some future model might also include general relativity, but expand upon it and make it more explanatory, more universal. My point of view is supported by my favorite little bit of early science, Occam's razor. Basically, Occam's razor says that things should be kept simple, and in fact, if you have some observations that can be explained by a couple of different ways, that the explanation that is simplest is likely the correct explanation. And then I found this quote from Lemaitre, to bolster my personal philosophy. He says scientific progress is the discovery of a more and more comprehensive simplicity. Sounds good to me, and hopefully one day we'll find the explanations out there, and hopefully they'll make the world simpler again. Thanks for listening.